Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject EC 3452 Electromagnetic Fields for 4th semester ECE students. Today, the topic is from the Unit 4 of EMF. The topics are time varying fields and Maxwell equations. This topic is one of the most important concepts in electromagnetic fields because it explains how electric and magnetic fields interact with each other. The work of James Clerk Maxwell unified electricity and magnetism into a single theory and laid the foundation for modern wireless communication, radar systems, optical fiber communication, and microwave engineering. Next, we see about the introduction to time varying fields. Before studying Maxwell equation, let us understand the concept of time varying fields. In electrostatics, electric fields are produced by stationary charges, while in magnetostatics, magnetic fields are produced by steady currents. These fields do not change with time. However, in practical systems, currents and voltages often vary with time. When electric and magnetic fields change with time, they become interdependent. A changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. This interaction is basis of electromagnetic wave propagation and forms the foundation of modern communication systems. Next, we see about the Faraday's law of electromagnetic induction. Faraday's law states that a time-varying magnetic field induces an electric field. Mathematically, the induced electromotive force around a closed path is equal to the negative rate of change of magnetic flux through the enclosed surface. The negative sign indicates that the induced electric field opposes the change in magnetic flux according to Lenz's law. In differential form, Faraday's law states that the curl of the electric field is equal to the negative time rate of change of magnetic flux density. This principle is used in generators, transformers, induction motors, and many electrical devices. Next, we see about the displacement current. The original Ampere circuital law was only valid for steady currents. A problem arises when we consider a charging capacitor. Current flows through the connecting wires, but there is no conduction current between the capacitor plates because they are separated by a dielectric. This creates a contradiction because current continuity appears to be violated. To resolve this problem, Maxwell introduced the concept of displacement current. Displacement current is not due to the movement of charges, but it is associated with the time-varying electric field. This concept completed Ampere's law and made it valid for both static and time-varying fields. Next, we see about the Maxwell-Ampere law. By incorporating displacement current into Ampere's law, Maxwell obtained the Maxwell-Ampere law. According to this law, magnetic fields are produced not only by conduction currents but also by time-varying electric fields. This law states that the circulation of magnetic field intensity around a closed path is equal to the sum of conduction current and displacement current enclosed by the path. This equation explains how changing electric fields generate magnetic fields and plays a vital role in electromagnetic wave propagation. Next, we see about the Maxwell's equations. Maxwell combined the fundamental law of electromagnetism into 4 equations. The first equation, Gauss' law for electric fields, states that the electric charges are the sources of electric fields. The second equation, Gauss' law for magnetism, states that the magnetic monopoles do not exist and magnetic lines always form closed loops. The third equation is Faraday's law. which states that changing magnetic fields generate electric fields. The fourth equation is Maxwell-Ampere's law, which states that changing electric field generates magnetic fields. Together, these four equations describe all electromagnetic phenomena. Next, we see about the physical significance of Maxwell's equation. Let us understand the physical meaning of these equations. Gauss' law tells us that electric charges produce electric fields. Gauss' law for magnetism tells that isolated magnetic poles do not exist. Faraday's law explains how changing magnetic fields create electric fields. Maxwell-Ampere law explains how changing electric fields create magnetic fields. These equations reveal that electric and magnetic fields continuously sustain each other, resulting in the formation of electromagnetic waves. This discovery led to the prediction of radio waves, microwaves, light waves, and all other forms of electromagnetic radiation. Next, we see about the potential functions. In electromagnetic analysis, solving directly for electric and magnetic fields can be complicated. To simplify calculations, we use potential functions. There are two important potential functions, the scalar potential represented by V and the vector potential represented by A. Using these potential functions, electric and magnetic fields can be calculated more easily. Potential functions are widely used in antenna analysis, wave propagation studies, and electromagnetic field computations. Next, we see about the scalar potential function. The scalar potential represents electric potential energy per unit change. The electric field can be obtained from the negative gradient of the scalar potential. This means the electric fields point in the direction of decreasing potential. The unit of scalar potential is volts. Scalar potential is extensively used in electrostatics and capacitor analysis. It provides a convenient method for calculating electric fields without directly solving field equations. Next, we see about the vector potential function. The vector potential is a mathematical quantity used to describe magnetic fields. The magnetic flux density can be obtained by taking the curl of the vector potential. Vector potential plays an important role in electromagnetic wave theory, antenna design, and advanced field analysis. Although magnetic fields can be calculated directly using vector potential, often simplifies mathematical derivations and computational methods. Next, we see about the applications of Maxwell equations. Maxwell equations form the foundation of many modern technologies. Wireless communication systems rely on electromagnetic wave propagation predicted by Maxwell's equations. Mobile phones, radio broadcasting, television transmission, radar systems, satellite communication, optical fiber networks, and microwave engineering all depend on these principles. Without Maxwell equations, modern communication technology would not exist. This is why Maxwell equation is often regarded as one of the greatest scientists in the history. Finally, we came to the summary of this lecture. Time-varying electric and magnetic fields are interrelated. The Faraday's law explains how changing magnetic fields produce electric fields. Maxwell introduced displacement current to resolve the capacitor problem and complete Ampere's law. Maxwell's four equations provide a complete description of electromagnetic phenomena. Potential functions simplify the analysis of electric and magnetic fields. These concepts form the foundation of electromagnetic wave propagation and modern communication engineering. Thank you, students. In next lecture, we will study the application of Maxwell equations in electromagnetic wave propagation and communication system. Thank you.